Hello everyone, my name is Jay Skaka and I'm going to be explaining problem 1 for Calc Assessment 3. So, problem 1 says a designer is making a box with a square base and open top as in figure 1. The box is made by folding up the edges of a sheet of aluminum in figure 2. She wants to minimize the amount of area used for the box that will have a volume of 1200 centimeters cubed. She wants to find both the minimum amount of material as well as the dimensions of the box with the minimum amount of material. So we can start by stating what is given in the problem, and we can see that the volume is given. So volume is equal to 1200 centimeters cubed. And then what is being optimized? It is asking for the minimum amount of material, so minimum surface area, and then we could draw a picture like they show in figure 1. And this is x, and this is also x, and then this is y for the height. So next we can find the relationship equation, which would be the volume equation. So to find the volume we would have to do length times width times height, which in this case would be x times y. So we can simplify that to just x squared y is equal to 1200. And for the optimization function, it's asking to optimize surface area. And the formula for surface area of the box would be 4xy, because that gives you surface area for all of these. And then plus x squared. Let me get rid of this. Okay, so next up we can combine them into one function. First off, we have to solve for y in the equation. So since we know that x squared y is equal to 1200, we could solve for y by dividing both sides by x squared. So then y is equal to 1200 over x squared. And then we could plug in to the surface, so the optimization function, and then we get surface area equals 4x times 1200 over x squared plus x squared, and then we can simplify that by multiplying 4x by 1200, and then we get 9600x over x squared plus x squared, and then we can cancel an x from the numerator and the denominator of the first term. So we're left with 9600 over x plus an x squared. So then we can find the derivative of the optimization function. So let me just rewrite the optimization function. And to take the derivative, it will be easier if we rewrite it with no denominators. So we could bring the x to the top by raising it to the -1 power. And then we can find the derivative by pulling the -1 out in front, multiplying that by 9600, and then dropping the exponent by 1. Then we do that for the second term as well. Drop the exponent by 1. So we're left with -9600 x to the -2 plus 2 x to the 0, which would just leave us with 2. We actually can take the derivative of the optimization function by bringing the -1 in front and multiplying it by 9600, and subtract the exponent by 1, then plus, bring the 2 to the front, x, drop the numerator, the exponent by 1, and then we're left with -9600 x to the -2 plus 2x. So now we can test for critical numbers since we have the derivative, and I can rewrite the derivative as -9600 over x squared to make it easier, and set it equal to 0 so that we can find the min and max of the original function. So first we would start by subtracting 2x from both sides. And since they're both negative, we could cancel them out. And then we multiply both sides by x squared. And then we're left with 9600 is equal to 2 times x cubed. Divide both sides by 2. X cubed is equal to 4800. And then we can cube root both sides. And then we're left with x is equal to 16.87. So now we can graph, and in red is going to be the original function, which is 9600 over x plus x squared, and then the derivative equation, which is -9600 over x squared plus 2x, and then we can insert the graph here. You could see that the red has a minimum at 16.869. So now we can find the dimensions of the box with the minimum amount of material, because since we have x already, we have x is equal to 16.87 centimeters. So we could solve for y using the relationship equation. So since x squared y is equal to 1200, we could divide both sides by x squared, and then we're left with y equals 1200 over x squared. And then we can plug in the x to the equation, 16.87 squared. Then we get y equals 1200 over 284.60, which is equal to 4.22 centimeters. So now we have x is 16.87 centimeters and y is 4.22 centimeters. So now we can find the minimum amount of material by using the optimization function. Which is 4xy plus x squared. So then we could just plug in both x and y to the equation, which gives us 4 times 16.87 times 4.22 plus 16.87 squared. And then we get 284.77 plus 284.60 is equal to 569.37 centimeters squared. And then that's our answer for the minimum amount of material that is used for the box. Hi, my name is Jay Skaka, and this is problem 2 for Calc Assessment 3. So problem 2 shows a graph R of t, and it shows the rate of volume as it is increasing and decreasing versus time. So A is asking, when is volume increasing? And the volume is increasing whenever R of t is greater than 0 or positive. So that is when t is from 0 to 5, as well as 7 to 8 because you can see right here the graph is positive and the graph is positive right here. Even though it looks like it's decreasing right here, it's really not, because since this is a rate, 4, like at t equals 4, the rate is still 1 inches cubed per second, as well as 2, it's still getting larger. So when is volume decreasing? And the opposite is true for this one. So whenever r of t is less than 0 or negative, and it's only really negative right here, which is when t is 5 to 7 seconds. Moving on to B. At what time is the volume of the balloon decreasing most rapidly? And that is at 6, because this is the most negative it is, the graph is, so decreasing most rapidly at t equals 6 seconds. Alright, C, find the volume of the balloon at t equals 1, t equals 3, t equals 5, t equals 7, and t equals 8. So we can write t of 1 equals t of 3 equals t of 5, t of 7, and t of 8. And we can see from 0 to 1, we can find the area under the graph to find the volume. So we would use 1/2 base times height, since it's a triangle, and then we get 1/2 times 1 times 2, it's just 1 inches cubed. When t equals 3, we are going to have to take t of 1 plus this area, which is 2 times 2, because base times height. So it's 1 plus 2 times 2, and that is equal to 5 inches cubed. On 5, we can find the area of this triangle, because this is 2, the height is also 2, so we take t of 3 plus 1/2 base times height, which is equal to 5 plus 1/2 times 2 times 2, and then that gives us 7 inches cubed. And then we take t of 5 for the next one, And we can find the area of both of these triangles by, and it's going to be negative since it's below the x-axis. So we would do minus 2 times 1/2 base times height, because there are two of them and in the same area. And that's 7 minus 1, which just gives us 6 inches cubed. And then we take t of 7 for this one, and we add 1/2 base times height over here, and it's 1 by 1, so we get 6 plus 1/2 times 1 times 1, and that just gives us 6.5 inches cubed. Now for D, it's asking to find, or to write the integral that represents the volume of the balloon at t equals 7 seconds. So we can write it like this, from 0 to 7 seconds. One half base times height plus base times height of the square plus 1/2 base times height of this triangle minus base times height of one of these triangles, and then plus 1/2 base times height for the last triangle. And as we got over here, the answer to E, we got 1 plus 4 plus 2 minus 1 equals 6 inches cubed. And then F. When is the balloon at its maximum volume? Let me get rid of all this. So we know that the balloon is at its maximum volume when it's done increasing over here. So that would be at 5. And we can also see right here, this is the largest volume we calculated. So at t equals 5 seconds. Alright, thank you all for watching. This has been Calc Assessment 3.